If you've ever built or operated a data system at scale, you've seen this pattern. Every new optimization idea starts out promising and then quietly dies under the weight of training cost, maintenance, and operational friction. This paper asks a deceptively simple question. Why does machine learning inside databases keep restarting from zero? And more importantly, what would it look like if databases learned the way modern data systems do, once, broadly, and reusably? The ideas I'm sharing here come from this paper, Towards Foundation Database Models by the folks at Google Research. Over the last few years, databases have started using machine learning internally. Things like query optimization, cardinality estimation, scheduling, storage layout decisions. These learned approaches often outperform classical heuristics, but they come with a serious downside. Today's dominant approach is instance-specific learning, which means one model for one task on one dataset. If you want to estimate query size, train a model. If you want to estimate runtime, train another. New dataset, start over. In practice, training a single one-off model can require running tens of thousands of queries that can take hours or days. And every model has to be maintained as data changes. For cloud providers, there's an added problem. They often can't even use customer data to train these models because of security constraints. So, despite strong results in research, adoption and production has been limited for these models. Now, this community has tried to improve this. Multitask models reduce overhead, but still require one model per dataset. Zero-shot models generalize across datasets, but only for a single task. What's missing is a model that generalizes across both datasets and tasks. The gap is exactly where this paper focuses. The core idea here is what the authors called Foundation Database Models, or FDBMS for short. The idea is inspired by large language models, no surprise. Instead of training a new model for every database problem, you pre-train a single general model that understands the structure of data and queries, not just any specific dataset. Then for each downstream task, you train only a small, lightweight model on top. The key insight is modularity. FDBMS are built as a team of composable experts. First, the data expert. This model learns general properties of tables, things like distributions and correlations, using a relative encoding that doesn't depend on specific values. That's what enables generalization across datasets. Next is a logical plan expert. This layer understands how relational operators, joins, filters, projections, transform data. It enriches the data representation with query semantics. And finally, the physical plan expert. This adds execution-level knowledge, algorithmic complexity, hardware characteristics, and performance behavior. Each expert builds on the previous one. Once these experts are pre-trained, you don't retrain the whole system for every task. Instead, you train a simple downstream model using the expert representations as input. And the paper shows that with just a few hundred queries, the system can match or outperform specialized one-off models on tasks like cardinality estimation and runtime prediction. That's a critical difference. Most of the intelligence is learned once and reused. For enterprise leaders, this has big implications. And first is cost reduction. You eliminate redundant training pipelines and expensive retraining cycles. Faster deployment is another benefit. New learned components can be rolled out in hours or days, not weeks. And finally, broader capability expansion. The same foundational architecture supports multiple tasks instead of requiring separate systems for each one. What's exciting is that this composable expert architecture could extend beyond databases into cloud resource management, workload scheduling, and complex systems. The future of intelligence systems isn't about smarter point solutions. It's about reusable intelligence built into the foundation. And that's what this work worth paying attention to. Link to the paper in the description below. And thanks for watching.